continue the topic. Right, so what we started last week and we'll conclude this week was the last transform that we are interested in terms of this course and in terms of what you're going to meet in engineering. The first one, the Laplace transform, of course, we met several times already, and you're going to keep meeting it all the way through until you graduate, which is the Laplace transform, of course, is for continuous time systems, and our purpose for sort of using the Laplace transform initially was because it provided us with a tool to solve differential equations. There's a lot of people may not be in class. Well, okay, well, it's recorded, but we have to finish off what we're doing here, so hopefully they'll be able to listen to it. I try to tell people, and we try to say that if you have things to do, you know, you come to class and it will help you. At least you sort of absorb the material and so on. But anyway, that's as it is. All right, so back to here. There's a recording, so they'll have a chance to listen to it. So what we saw is that continuous time signals or continuous time systems are described by differential equations, and you solve differential equations by either going through a lot of integration and processes and so on, and in some cases you still have to do that, or if the conditions are right, you can apply the Laplace transform to it, and it converts the solution into a fairly, well, relatively simple, I should say, algebraic form. What we do as engineers and as engineering students, we get so used to describing everything in the S domain. So we talk about transfer functions and so on, and everything is in terms of S. Even when we're describing, like in electronics, when we're describing filters, we describe them in the transfer functions in terms of S. You know, low pass filter, high pass filter, there's a S and a S squared, and we talk about the poles and the zeros and so on. But we sometimes forget that the transfer function in S, in the S domain or the Laplace domain, is really just a stepping stone, that we could do everything that we want there to see how the thing behaves, and but at some point in time you have to come back to the real world. What is y t in terms of xt, for argument's sake, you know, and that is the solution to the differential equation and so on. And that is the time behavior that we're trying to seek in real life. We also saw the Fourier transform, which was a way of looking at the same system, but from a different angle. And that gave us frequency information. Instead of the time-based information that they get from the Laplace, you get the frequency-based information by using the Fourier transform. All of those, both the Laplace and the Fourier, apply to continuous time systems. There's a whole world of systems, though, that are not continuous time, they are discrete time. And how you get to a discrete time system is that you take the continuous time world, usually, and then you sample it and convert it into a set of numbers. So the discrete time world is described by a series of sampled values, and we process those values in a particular way. What we saw last week is that the discrete time world is described by something called a difference equation now, right? Difference. A difference equation as opposed to the differential. The difference equation means that the output answer, which is a sequence of values like a y, let me put it in square brackets, kt, right? That the output is usually in the form of a series of previous inputs, right? kt minus nt, a whole series of previous inputs plus all of the, sorry, a whole series of previous outputs plus a whole series of inputs, right? In general form. And the analogy that I brought to your attention was in your digital electronics, that you have met things like counters. the output of a counter is a function of what the other state, what the previous state of the counter, state or states of the counter is, plus the input. The input here might be a clock signal or a signal that tells you to go up or to go down. This will be what the previous count is. So if the particular count is 0, 1, 0, let's say you have a 3-bit counter, the next count in that should be 0, 1, 1. That, to get to here, which is your YKT, depends on the previous value, which is this, plus some input that will tell you, okay, go count up or count down. All right, that type of approach, that type of description is what we call a difference equation. And to solve a difference equation, we needed a different tool, which is where the Z transform came about. It is specifically designed to work with discrete information, sampled information, and the form of it in general looks like this. It's a power series, so that the Z transform of a series of values or a sequence of values is simply that multiplied by this complex variable Z to the power minus K, and you're counting from minus infinity to infinity. This is the two-sided, right? If XKT is causal, meaning that K starts at 0, then we could change the order of summation, or the lower limit of the summation to 0. And in this case, now we create what is known as a one-sided Z transform. And this now is basically, if I were to expand the one-sided Z transform, all this is a sum. So it is X0 by Z to the 0, or minus 0, however you want to put it, plus X1 Z minus 1 plus etc. X2 Z minus 2 and so on. It is a power series in Z to the minus K. And we also said that, remember, the mathematicians prefer the conventional operation of it. So this will be 1 over Z to the 0. This will be 1 over Z. This will be 1 over Z squared. And so you keep going on, all right, by the same X0 here, X1, etc., etc. Right? So that's where we, and we looked at a couple of examples after that. What we said is that from an engineering perspective, this means something to us, and we'll meet it in a short while today, actually. At least introduce what it means. So we prefer to keep the Z transform with the negative indices. The mathematicians and the math books and so on tend to use the positive indices for it. But as we saw, it's fairly easy to convert from one to the other. And again, between today and tomorrow, you'll see, depending on what you're comfortable doing, you can go from one to the other, right? The Z transform tables, like how we have Laplace tables and Fourier tables and so on, the engineering books will give you the tables in terms of Z minus 1, okay? So everybody remember, at least recall some of this, I hope. So we looked at spoke about this. This was just the fact that it is a power series, and for this to have a finite sum to infinity, right? There are certain conditions that have to exist so that this will actually have an answer, all right? And we mentioned that just generally, but it's just for you to be aware of as you go through your engineering career and wherever, if you go on to do postgraduate work and that kind of thing, it will come up again that these things, some things may not have a Laplace or a Fourier or a Z transform because it doesn't satisfy the conditions, okay? Just keep that in the back of your mind all the time. And you will always see it if you go to a textbook or you go to online, a set of tables and so on. They always tell you, well, yeah, this has a transform, and then there's a particular set of conditions on it. All right. We did the Z transform of the unit pulse, which is 1. We did the Z transform of the unit, the discrete unit step, which was 1 over 1 minus Z to the minus 1. And then we did a little bit of manipulation to find out, well, when does this series converge? And we drew back on some knowledge from your AdMaths and your calculus days that this will only have a sum to infinity if the common ratio is less than 1, right? So this little formula here only convert, this whole thing here, A is the first term, only converges if R is less than 1, or mod R to be more, if we're dealing with complex variables, that the magnitude of R has to be less than 1, otherwise this thing can't converge. And if we apply that here, right, we found that the region of convergence was a particular zone that we call the unit circle, a circle of radius 1, right? So whenever I tell you mod Z is greater than 1 or mod Z minus 1 less than 1, if I put the equality here instead, if I tell you mod Z equal to 1, mod Z equal to 1 is a unit circle. Remember, this is a plus JB. So if this is equal to 1, the magnitude of this complex circle, of this complex number is 1 all the time. It means that it's tracing out a circle. And because we're dealing with another transform, like the Laplace transform was the S-plane, right? So you plotted that, the S-plane had a real and an imaginary part. So the whole S-plane was the Laplace transform. If we remember, we can get some Fourier transform information by making the substitution S equal to J omega. Where is S equal to J omega? S is equal to J omega on this axis here. So in other words, even on the S-plane, the Fourier transform is what happens up and down this axis. This is where S is equal to J omega. So in other words, if you take the Laplace transform and make sigma 0, you get the Fourier transform. In the case of the Z transform is in a plane called, of course, well, the Z plane. And instead of a sigma and a J omega, they describe the Z transform in terms of polar coordinates instead of Cartesian coordinates. And you have whatever it is, you have the magnitude of Z, and of course the argument of Z right here. Okay, and we just made some. Everybody recall that, or you had any questions? We did it. Any questions on this up to this point? We spoke about all of this in class. And what we saw, the last thing I spoke about is that the S-plane, that the left-hand side of the S-plane mapped inside of the unit circle. This, the stability business about all the poles of a transfer function, a continuous time transfer function, being in the left-hand side of the S-plane, we explained that already, which we said is that if you remember that the e to the minus st for the Laplace transform is really e to the minus sigma plus j omega t, which is e to the minus sigma t by e to the minus j omega t here. This is just a complex sinusoid, so you could ignore this. This just goes up and down between positive and negative 1 maximum. This is the part here, right? And we saw that if for the thing to be stable, that you want it to be on the left-hand side, because then the e to the minus sigma, right, would make the answer converge, right? That would be a decaying exponential and so on. This bit of mapping here, not to worry about it, but you're going to meet it in control systems, especially if you do advanced controls, where what they do is that they take a continuous time system and they sample it to make a discrete time. So you will meet that at some point in time, this whole thing about the comparison between the S-plane and the Z-plane. All right. We will talk about it. The lectures that I asked you all to listen to explains it a little bit. All right, about why we want the poles in these particular positions and so on. But the use of this is specifically for when you're going to do control systems, and especially advanced control systems in year 3. Okay, if those of you who will be doing that. Okay, so bear it in mind. It will come up again. You will have to go back and find your notes here for it briefly, and so on. All right. Right. So the other one, of course, and we could end with this quick example and then go on to what the other part of the lecture today. What about this? If a sequence of numbers is a to the power k, right? So a to the power k, a is a real number or complex number. So 2 to the power, let's say 2 to the power k, right? So that series of numbers will be 2 to the power naught plus 2 squared plus 2 cubed, just for argument's sake, right? Which is 1 plus 2 plus 4 plus 8, etc. So if there is an exponential type of sequence, what is the Z transform of that exponential type sequence? Well, of course, the one-sided Z transform. This is x, k, oops, kt here, zk. So if you expand it out, you get, when k is 0, you have 1. K is 1, you have a z to the minus 1. K is 2, you have a squared z minus 2, and so on. Or the math books will tell you this: a over z plus a squared over z squared plus a cubed over z cubed. All right? Right? So there's the math book. What is the sum to infinity of that? Well, again, the common ratio is a z to the minus 1. So that the sum to infinity is a, which is the first term. Well, I shouldn't use a actually, because a is inside of here, but the first term over 1 minus r. The first term is 1 over 1 minus r. Okay? So you could have it in this form, or as I said, the math books will have it in this form. And it's very easy, as we said, we could move from here to here. If I take this 1 over 1 minus a z, z minus 1, if I multiply this by z over z, z over z is 1. All right, so if I multiply this, what I would get is z over z minus a z minus 1 by z, which is this answer here. All right, so you could move back and forth between the positive and the negative indices to your heart's content. But the engineering version we want is to retain this form, okay? Fair enough? And the region of convergence, of course, the common ratio, which is this, has to be less than 1. So in other words, if you were to draw it out, the common ratio mod a z minus 1 has to be less than 1. This translates into z mod z being greater than mod a. All right? This is the unit circle here. So mod a, mod z greater than mod a. This is a circle of radius a. I don't know what the value is, right? It could be inside or it could be outside a unit circle, depending on what that is, right? So this is a circle of radius a. This is the unit circle, which the radius is 1. So depending on the value of a, the region of convergence will be inside a unit circle or outside a unit circle. All right? Okay, you're going to meet that elsewhere, as I said, but just remember that the Z transform has a particular region that it has an answer, and a particular region that it doesn't. That's all you have to remember. Okay? So any questions on that part before we move on to some of the properties? We need to look at one of the main properties of that. That was the sort of core lecture topic today. We all right? Yeah, no, it's coming out to the end of the semester. So again, review the material. Don't wait 2 weeks before the exam when they come down, because this is the last. If you're revising for the final exam and you're waiting until sort of you only get to what we're doing, the last topic, you get to that for the first time 2 weeks before the exam, all of this is going to sound fairly strange to you. So you have to review this even while you're doing your revision. Okay? Just my advice. It works better that way. All right. So let's look at the other part here now. So many of the, because of the sort of applications and so on, the Z transform has properties like the Fourier transform, like the Laplace transform, that are sort of similar in nature. So there's a property for shifting, scaling if you multiply it by n, cosine, sine, and so on. But what we really, and just this last one here, like the Fourier and I like the Laplace transform, the convolution, you remember x, t, convolve with h, t in continuous time is x, s times h, s, or you could even use the Fourier x j omega times h j omega. The same thing happens in this Z transform, that the convolution of two sequences, xn and hn, is the multiplication of the Z transforms of each of them. So the same sort of advantage that they get, that we got in the continuous time domain, the Z transform is giving us in the discrete time domain. All right. Again, you don't have to do these. This is not, you're not going to get any questions on this even all the way down here. We'll meet convolution if you ever do signal processing in year 3. We're going to talk about that a lot. This is the one that we're going to zero in on a little bit. All right. So our focus is on two versions. Instead of two properties here, is really sort of two versions of a single property. All right. So maybe you could have focus on single property, two versions. All right. So if you want, and this is the first version, and this is the second version here. So the first version of this property, and this is the key to everything that we want to use this transform for, is that if I have a sequence of values and I delay the sequence of values by some number, okay? So like, for instance, I have 1, 2, 3, 4, right? So x, kt is equal to these 4 values, okay? Let's say I delay all of them. So I plot it here. So x0 is 1, x1 is 2, x3 is 3, x4 is 4, right? If I delay it by some amount, so I shift everybody down by some, let's say by 2t, okay? So the sequence is now, remember, what does this mean? Whenever I take a sequence and multiply it by unt, what does that mean? If ever you forget, if I take for my continuous time domain xt and I multiply that by ut, what does that do? What does that do to xt? Quick, there's easy revision. If I take a continuous time signal and I multiply it by a unit step, what does that do to the signal? It makes a signal what?
Causal, sir.
Nice. Correct. By multiplying anything by the unit step, you make the signal causal. So if I take this sequence here, right, and I multiply it by UKNT, what I'm doing is making this, whatever the first value of this, I'm making, making that a causal signal, right? So I'm saying I have nothing before here. That's all this is saying. If I do that and I delay, this property is saying that if I do this and I delay everybody by some value n, I'm just using the value 2. So in other words, I will prove this formally in a little while. I kind of jumping the graphics here a little bit. So by delaying it by 2, it means that it's now, the first value is not, the second value is not, the values start 1, 2, 3, 4. Right? So that is now, this is now x n t minus 2. Fair enough? Make sense? I just delayed it by 2. In other words, I shifted it to the right, if you like. So how it looks like is that this is 1, this is 2, this is 3, this is 4 now. Right? So I shifted these red values, shifted them down 2 units. Make sense? Yeah? Good. I have the values 1, 2, 3, 4, right? Which is what I have here. 1, 2, 3, and 4. I delay this entire sequence by 2 time units. So in other words, I have taken this, whatever this value here is now here. This is 2 units down. This is not 1, 2, 3, etc. So this value has gone to here, this value gone to here, this here, this here, delayed by 2t. Yeah? Make sense? Just that particular shifting. Is that clear now? Right, good. So once I do that now, what this property, the first version of the property is saying is that the Z transform of this now, which is the delayed version, is the same Z transform of this, and I multiply it by Z to the minus whatever was the amount that I delayed it by. So since I delayed this by 2, this Z transform, if this had a Z transform X Z, then the delayed sequence has a Z transform Z to the minus 2 XZ. Right? That's all that property is saying. Fair enough? So if you take the sequence and you delay the sequence, right, this one is the causal version. Right? This one here, because of this unit step, this is the causal version of that. The second property, which is a non-causal version, says that if I delay it by a certain amount, the Z transform is Z to the minus n, which is like this, but we're going to have some other values to take into account. And we're going to prove that formally. If you want to recall, remember the Laplace transform that y t gave me ys, dy dt gave me sys. Right. This one is saying, you remember that the differential in the continuous time domain corresponds to the difference in the discrete time domain, which is this here. The differential in the discrete time domain, in the continuous time domain, corresponds to the difference in the discrete time domain. So just like how if you had yt giving you ys, dy dt, which is a first derivative, give you an sys. If you had xkt, then the difference, the first difference, for instance, will give you z minus 1xz. The second difference or delay would give you z minus 2. That's what that's saying. Yeah? Let's prove the properties now. Right? And you'll listen. And then we'll go back over. So let's say that, as we had before, we have a causal sequence of numbers. And we want to prove that the Z transform of it, if I delay the values by some amount nt, that the Z transform, this had an original transform of xz, that the delayed version has a transform z to the minus nxz. How we prove it? Well, very simple. If I give you that ynt is this thing here, the z transform, of course, is the z transform yz is k equal naught to infinity y nt z to the minus k. So I just substitute ynt into here, which is this bit here. And we have, this is the expression now. So what is that? What does that look like? Here are some graphics here. So on top here, this is what we were talking about. On top, look at the upper thing. I have some thing xkt here in red, and I have ukt. Where's my pointer? ukt is the unit step, some strange, right? And ukt is the blue bit here, right? If I multiply any signal by a unit step, what it does, it converts it, as somebody correctly say, it makes it causal. So by converting it, by multiplying the two, this is what I now have. xkt by ukt is just these values that I have here. So if I delay it by some amount, xkt minus nt is this red stuff shifted down by some amount n. We just went through that, right? xkt minus n is this values here shifted or delayed by some amount n. And if I multiply it by the same ukt shifted by that amount, that's the same blue things shifted to the right, is going to take out, you have the unit step here, and it's going to shift that all the way by the same amount as well. Multiply the two of them, what do I have left? It's going to take away all of these values here. So this is what that is what that expression means. What is the Z transform of that? This is what we have here. We could change now, if I let m be k minus n. If you're getting confused, you can always put this as k minus n, right, into u k minus n here. All right, you could forget the capital T is understood all the time. So if you want, so now let me change this inside of here to some new variable m. So I have x m, right, u m, but then now I have to change this here. So if I let m be k minus n, then k is simply m plus n. So I could substitute that here, z minus, and instead of that, instead of k, now I have m plus n. All right. Of course, I have to change the here now. The lower limit will now, because I'm now changing everything in terms of m. Why am I doing that? Is to get it into this sort of standard form that we have. So if I change k, I have m equal to minus n. This is the summation here. But remember, it's a causal signal. So m really m doesn't have any minus n values. If you look at it, the thing is causal. So we have no values less than 0. So I could sum this from 0 to infinity. And this is what I have. Notice that this now is x m z minus m, and I have a z to the minus n inside of here. The summation is m, so I could take this out. So this is just simply z minus n into x m z to the minus m. And this is the definition of the z transform. That is just simply xz. All right? Make sense? It's some simple algebra. All I'm doing is to take once you understand this, then the other part here, changing the variables, finding the z transform of it, is very easy. You're just changing the order of summation. Yeah? Let me know, does it make sense? Yeah, no? All right. So step one was to understand what this is. All right. What is that? That is a delayed causal signal. You multiply anything x kt by u kt is a causal signal. This is the causal signal delayed by n. All right, the t is understood. So if you're having difficulties, you can just take out the t. If you're looking a little too complicated, just take out the t. So x n u n is causal. X n or x k uk is a causal signal. xk minus n is xk delayed by n, but if you multiply it by the same unit step, delayed by the same amount, then it is just the same causal signal delayed. And the z transform of that, right, is the original z transform, but because you delay the whole causal set by z, by n, you have to multiply this by a z to the minus n here. All right, this is the the equivalent of the Laplace transform version, where if you have y giving you ys, then dy dt will give you sys. All right? Why? Because we said that the difference, you remember, a difference equation is just a set of delayed values. So if I tell you y n t equal y n minus 1 n minus t plus something, this is a delayed version of that. Like your counter is the previous value or the previous set of values. This is what we, and this is what we call the difference equation. So the Z transform of this is just simply Z minus 1 YZ. Okay? Make some sort of sense? Yeah? Come on, give me some ideas so I'll know what if I'm losing you, or if it is at least there's some clarity in what we're doing. All right? Okay, Carolyn, thank you. The other version now is, what if we're not dealing, right? What if we are not dealing with our causal signal? Why? Because, as we said, discrete time signals, a lot of them you can store. So like music signals or the counter. The counter, for instance, the 3-bit counter starts 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, etc. And it goes all the way up to 1, 1, 1, and then we'll presumably could start back over. If I start looking at the value here, for a particular 3-bit counter, if I look here, there is a value before I started to look at it that it exists, and one before that, and one before that. This particular version, therefore, if I start looking at a counter, a set of values from a counter, the values could be non-causal because they were values that existed before I even started to look at it. So if the counter is at count 4, right? Previously, before I started looking at it, it was at count 3, 2, 1, and 0. Unless I specifically started it at count 0 or at count 4 and nothing else, right? If I loaded that value into it, which is possible. If I did that, then that is one thing. But if I didn't, then the counter value could have, the counter could have previous values. All right. So if I look at a non-causal signal, if I have a non-causal signal like this now, right? So all of the values here, all of these values here represents my xkt. If I delay this now by 1, xkt minus 1, it means that everything, a delay is a shift in time this way. So xkt, right? Forget that block for the time being. xkt minus 1, right? Or xkt minus t, remember the t is understood, is the entire set of values shifted to the right by one sample. But notice what happens when I do that. If I shift everything to the right, remember this is not causal now, non-causal. If I shift everything to the right, notice this value here, which is x minus 1, is now here. This is my t0 point here. And this was 0 here. So everybody here to the right of 0 goes 1 unit, 1 time step over, and the x minus 1 value now becomes the 0 value. It now comes into the count. Okay, go back up to the top now. What we just did, xkt had a one-sided Z transform of XZ. So XKT, all of those in the dotted box had a Z transform of XZ. Notice that is the same set of values here. We've delayed them down, we've delayed it by 1. And from the previous set of, this little discussion that we had, if I delay it by 1, then the blue guys will be the same XZ, but we have to multiply it by Z minus 1 because I've delayed it by 1. But because we know dealing with a non-causal, I'm not multiplying it by any unit step here. I now have to have the Z transform of this value here because I'm summing from 0. So that this particular one is Z minus 1 XZ plus the Z plus that value there now. Right? And of course, well, there's a transform of that particular first value, which would be Z to the power naught by X minus 1. Okay? So this now starting to look at what happens if I delay, if I don't have a causal signal. The causal ones was easy. If I delay it by some value, I just multiply XZ by a Z to the minus whatever that delay was. So we're now looking at what happens now if I'm not dealing with a signal that is causal. You shift it by 1, it's the same XZ, but you have to bring in an initial value. So if I were to delay by 2 now, delay by 2 samples, this group, this has a Z transform XZ. If I shift everybody by 2, notice the same group here. So this will be Z minus 2X minus 2XZ. But I now have to bring in these 2 values because I'm summing from 0. Remember the Z transform sums from 0 going forward. So I have to now bring in these 2 initial values inside of there. All right, that is the second property, and we will talk a little bit about that tomorrow. Right, just to review it. But the analogy is this. You remember in your Laplace domain, when you had the Laplace transform of something with initial conditions. So y t give me dy dt give me without initial conditions gave me s y s. If I had initial conditions, you remember I had to put in y0 minus inside of here. It's the same sort of thing. And d2y was s squared ys minus y prime sy prime 0 minus y at 0. Okay, the same thing. This is why I was saying that it's not entirely new material that you're doing. So it's the same sort of process here. Okay, we will go over this again tomorrow's class, but I wanted you to get the idea because this is the crux of the whole matter for what we want to do with the Z transform, which is how to solve a difference equation. Right? So if this just in summary, right? X and T, X and T gives me XZ. X and T, U and T, right? If I delay this by any amount, K, meaning that there's a causal, then what I have is z to the minus kxz. If it is not causal, then x nt minus k, I have my z minus 1 xz, but I have some other values that I'm going to have to bring in inside of there. If it is 1, if k is 1, then we have a z naught x1. If it is 2, then we have something looking like this. If it's 3, and we'll keep expanding. All right, we'll go over this again tomorrow and then see how to use it to solve a difference equation, and then how to get back the answer in terms of time and so on. All right, so think about it, listen to the material, and then when we come back tomorrow morning, we will tomorrow afternoon, sorry, we will run it through again. Okay, no, for those of you doing electronics, no electronics class this afternoon. Tomorrow morning, we're going to have a revision class. I'm preparing just some slides, some general revision slides to sort of summarize the material that we did. I've put up a problem set for you so you could start looking at that as well. Okay? So everybody all right? Yeah? Okay, so let me